Okie dokie. Let's push straight on into simple harmonic motion. Just a reminder of timings. We are aiming for a lunch break to start at 12. And so let's push on through. We're going to cover circular motion, and then it's analog simple harmonic motion. Those two types of motion are different, but they have mathematical similarities, and that's as far as it goes. So don't sort of say that they're the same thing. Because that always annoys physics teachers, and that always annoys physics examiners. Okie dokie. If we are talking about either of these, we are going to need to establish some mathematical ground rules, and that's the language of radians and angular velocities and things like that. So, just to clarify, for those who don't know, a radian, it's an angle. So instead of splitting a full rotation of a circle into 360 degrees, as you probably are used to, the concept behind using radians is instead just splitting it into 2 pi pieces. 2 pi is a number like any other. It's a very specific number, but yeah, you are splitting a full rotation into 2 pi radians. Why? It is calculated such that when you use radians, 1 radian is the angle formed by a circular arc at the center of a circle when the arc length is equal to its radius. This is not a fantastic drawing of 1 radian, because 1 radian is, from memory, roughly equal to 55 or something, 57.3 degrees. So that's roughly what 1 radian looks like. And in my drawing, you can see, look, 1 radian is calculated such that this red length here, if I change my ink color, is exactly equal to my arc length here. It's probably annoying a few of you that I've used ink colors different to displayed here, because S would be this length and R is the radius, and this theta is equal to 1 radian. So when you draw a Trivial Pursuit wedge, and you such that the radius is equal to the arc length, that means you've got yourself 1 radian. And that's the definition. Everything else follows on from that. If you do the maths, you'll find that that means that you can fit 2 pi radians in 1 full rotation. So if 360 degrees fits in 1 full rotation and that equals 2 pi radians, that also means 180 degrees is equal to 1 pi radians. And so if you're converting between them, your conversion factor is 180 over pi. Fab. And obviously, 1 degree is very, very slim, but 1 radian is actually quite chunky. So if you're converting between the two, make sure that if you're converting from radians to degrees, you end up with a bigger number because it's a smaller unit. And if you're converting back the other way, you're going from a smaller unit to a bigger unit. So your number should be smaller. As long as that's in your head, you shouldn't go wrong. We say that an object is periodically traveling at a constant speed in a complete circle if it's going uniform circular motion. Okay, so this is the great tension at the, no pun intended, but that's the great tension at the center of circular motion, is that your speed can be constant. You're traveling around in the circle, uniform circular motion, but your velocity is constantly changing. And so your acceleration indicated, so the force, the tension in this string is indicated by the green arrow, but it also indicates the direction of the acceleration. Whereas this purple trajectory is where its displacement and its velocity will be pointing. At a given amount of time, its velocity will be pointing that direction. So if we're spinning a bob, whirling it around our head, hooray, great fun. It's moving at constant speed, but its velocity is always changing. So at one moment, it's got a sort of velocity that's pointing in this direction. Let's call that v1. And then at the next moment, it's pointing this direction, v2. Velocity is a vector. And so you might well ask, well, how did we get from v1 to v2? Well, we must have had a change in velocity, and we have. A change in velocity is what acceleration means. And here it is, a little acceleration. It's a vector. And where does it appear on my vector diagram up here? There it is. The acceleration points this direction on my diagram, and lo and behold, it points in the same direction on my vector diagram. Because acceleration is a change in velocity per unit second, or per unit time, that's exactly what's going on. We go from v1 to v2 via this acceleration. Okay. Now, of course, in the next second, well, the acceleration has now changed direction as well as the velocity, and so you're constantly playing this game of cat and mouse around the circle, where the velocity is always changing because the acceleration makes it change, but that means that the acceleration also has to change for the next moment, and so on and so forth. The bob is accelerating. Don't forget that. This is centripetal acceleration. Okay, I said that this part of the course was about establishing a few mathematical ground rules. An important concept to understand is angular displacement. So just as we might talk when we talk about linear motion, we'd talk about regular displacement. We'd say, look, that's it, you've traveled 2 meters in that direction. Angular displacement is the same thing, but it's just talking about how much angle you've traveled through. Okay. So just as you can travel 8 meters or x meters, you can rotate theta radians. Period, hopefully a concept you've met before, indicated by t, is the time to do a complete cycle. Angular speed, again, by analogy to linear motion. In linear motion, you can say, well, okay, you've gone x meters. What if you do x meters per second? That's now velocity. Switch back to your angular analog. Okay, you've rotated omega radians. What about if you rotate omega radians per second? That's angular speed. So it's rather than just a single step in a direction or a single rotation, it's if you're doing those every second, so on. So you're really enacting motion. Radians per second. Fab. Briefly, if the period is the time to take one full revolution, how many revolutions do you per second? That's the frequency. It is going to be 1 revolution per period is going to be your frequency. The angular speed then. If you are doing let's say 3 full revolutions per second, how many radians are you turning in per second? Well, you're doing 2 pi and 2 pi and 2 pi. So you're doing 6 pi radians per second. How did we get that calculation? Well, we simply multiplied the frequency by how many radians there are per revolution, 2 pi. So if you're ever given the frequency of circular motion, you can work out the angular speed by simply multiplying it by 2 pi, the amount of radians in 1 revolution. And the definition of this angular speed is a change in angle over a change in time. Instantaneous velocity, v is the velocity component tangential to the circle in meters per second. Yep. Okay. So far I've been talking about linear motion and angular motion almost separately. So how can we link them? This is why radians come in useful. If I turn 1 radian per second, we defined radians as the angle such that the arc length is equal to the radius. Therefore, however many radians we're turning per second, the angular speed, if we simply multiply that by the radius, that is going to be our linear velocity, our linear speed. Okay, that's not necessarily a derivation, it's just an explanation. But get this equivalence into your head. That is a really useful conversion to be aware of. What are the corollaries of this? Well, we know that omega is 2 pi f, so I could write this as 2 pi fr, which means I could write this as 2 pi r over t. Does that make sense? Yes, it does, actually. If you think about the mathematical format of this, you're saying 2 pi r. Have you seen that before in maths? Yes, we have. That's the circumference of a circle. And so the period is how long it takes to do a full rotation. And I'm saying, however long it takes to do a full rotation, you're going to divide the circumference of that circle by that number. This equation, v equals the circumference over the time it takes to travel the circumference. That's just velocity is equal to distance over time. You know, year 7 maths, but in a circular context. Okay, hopefully that wasn't too confusing. It's important to get a sort of really solid understanding of exactly what's going on with this angular speed and how it relates to linear speed. Okay, let's push on. The Earth orbits the Sun at a distance of approximately 150 million kilometers. Estimate the angular speed and instantaneous velocity of Earth. Okie dokie. We want the angular speed. We're given the radius. And it's 3 marks worth, which is quite generous. Yep. What we really want then is perhaps the period. Do we know the period? Well, yeah, actually we do. From primary school geography, we know how long a year is, and that's how long it takes for the Earth to orbit the Sun. It's 1 year. That's not the most convenient unit. Convert it to seconds. And they've even been assiduous enough to include leap years, 365.25, but they're not including leap centuries, but that's fine. Right, angular speed in terms of period. Yep. So we're interested in working out the angular speed. So we've got it in frequency there. Let's write it in period. We know what the period of the motion of the Earth around the Sun is now. So we've got the angular speed, really. And in fact, we didn't need r to work out the angular speed. It's when we're asked for the instantaneous velocity that we'll now need it, because we have just said that the instantaneous speed is the angular speed times the radius. Okay, so get your answer from the previous part and just multiply it by r. Okay. Centripetal force. Okay, so this is the force that is responsible for our circular motion. For an object moving at a constant speed v at radius r, there's a central piece of acceleration. And for the most part, just take this as given that a is equal to v squared over r. Yes, we can talk about its derivation in a context where we have more time, but sadly, we're going to have to push past it. That's in your formula books, but you should try and remember it yourself. It saves much time if you have it to hand. We can also express this in terms of angular velocity, because we know that v is omega times r. So let's say that's omega r squared over r. Expand that out, and we end up with acceleration is omega squared r. This acceleration has an associated centripetal force, which always acts towards the center. In this case, it's tension. In the case of our good hammer throw bro, it's hard to know from this diagram what direction he's swinging his hammer, but I'm going to say it's going around this direction. So our instantaneous velocity is there, but the force is pointing to the center and the acceleration is pointing to the center. And these are perpendicular. Okay. Which has the curious result that the force, the centripetal force, isn't actually doing any work done. I forget whether we cover that later on, but work done is only equal to the force times the distance moved in the direction of that force. Yes, the object's moving, but it's moving always perpendicular to the force. Okie dokie, F equals ma, and so this centripetal force, Fc, is mv squared over r, or omega squared r. Sorry, I didn't mean for that extra little bit. Okay, and again, those expressions are also worth remembering. It's worth, as soon as you see a circular motion question, you can say, I know what the force is. It's mv squared over r. Centripetal force is not a force which can act on its own, but it's always provided by some other force. Yep, so tension in a spring, gravity, maybe even electrostatic attraction or friction. Somebody standing on a roundabout in a play park that's slowly turning. Or yeah, normal reaction force. We've got these walls are pushing inwards. Tension here, normal reaction force, gravity. Okay, let's have a look at an exam question. The London Eye completes a rotation once every 30 minutes. My goodness. I've never been on it, but that's a little painful for me. While rotating constantly and has a radius of, well, maybe I'd like to go. Yeah, tell you what, I'll give it a second chance. Has a radius of 67.5 meters. Find the magnitude of the force that acts towards the center of the London Eye on a carriage that has a mass of 1,000 kilograms. Okie dokie. Our command word is actually find here, but it's a calculation question because it's asking for a magnitude of a force. 3 marks. Okie dokie. London Eye. It's essentially a big Ferris wheel. They give us the radius. They give us the mass of a carriage. And they are telling us that the period is 30 minutes. So 30 times 60 seconds. So straight off the bat, if you've got it dedicated to memory, you can say, well, the force is mv squared over r. Do we know v? No, we don't, but I know that v is equal to omega r, so I can do it in terms of omega instead. And you can then say, well, I don't know what omega is. But omega is equal to 2 pi f, which is equal to 2 pi over t, and we do know what t is. So we can express this whole equation in terms of t. Here we've been somewhat unrelentingly algebraic. It's a matter of style. It's up to you whether you want to do it all in one line or do it in several separate equations and then combine them. But I assure you, if you replace v with omega r and then replace omega with 2 pi over t, and then you square the whole thing and plug it into that expression, you end up with the circled expression. Put in your values, make sure you don't make a mistake, make sure you watch out for units, and then make sure when you put your answer that you include the fact it's in newtons. They've asked for a force, So give them a force. Give the examiner what they want. Okay, circular motion examples. A car going around a roundabout, yeah, it's going in a circle, hence it's circular motion. I know it's not a traditional example, it's not, you know, perhaps the centripetal force is not obvious, but in this case, if my car's going around this way, the centripetal force will be acting this direction. There's friction from the tires. Okie dokie. So, the following pattern of answering a question is going to serve you incredibly well. Often, what a calculation question for circular motion boils down to is you've got the equations for general circular motion, F equals mv squared over r. So that's in one palm of your hand. And in the other palm of your hand is what is the source of this circular motion? Is it friction? In which case it's the coefficient of friction times the normal contact force. Or, next mode, is it gravity? In which case you've got Newton's law of gravitation, Gmm over r squared. Or is it tension in a string? In which case they'll just give you the tension. You've got the cause of the force in one hand, and you've got the mathematical expression of the fact that it's a circular, it's creating a circle in this particular instance. You set those equal to each other and solve. And that's pretty much the recipe for a good 80% of circular motion questions. It's just this. Set the equation for circular motion equal to whatever the force happens to be in this particular instance. So let's do just that. mv squared over r equals mu r, where r is your normal contact force and mu is the coefficient of friction for those not in the know. Okie dokie. The coefficient of friction, not the coefficient of friction, yeah, the normal contact force. In this case, the NCF, it has nothing else to balance it out except the car's weight. And so this is going to be equal to the car's weight. Therefore, it's going to be equal to the car's mass times little g. We've got mv squared over r. The masses cancel. And if the question, for example, was, can you calculate what the how fast the car, what's the maximum speed the car can go whilst these forces are still balanced? You've set them equal to each other. So, you know, you're maxing out these forces. Solve this equation, multiply the r across, so you get r mu g, then you'll need to square root it. There you go, Bob's your uncle. That can score you, you know, somewhere in the region of 3 marks just for the same mathematical pattern applied again and again and again and again. So we love circular motion, really. This is perhaps an example, the only example that often comes up where it's a little bit different. If you're given the dreaded carousel, the complication here is that weight always acts downwards. Weight is not always, it doesn't consistently play the role of the centripetal force. Sometimes it acts in alignment with it, for example, at A, but sometimes it acts against its interests at C. What needs to take up the slack then and counteract the weight and then go some more is the tension. So at point C, the tension is going to have to be really big because not only does it need to support the weight of the carriage, but it also needs to provide some centripetal acceleration. But at A, the tension will ease off. It doesn't need to do so much pulling. It might still contribute a little bit, but as long as the vector sum of the forces on each carriage is constant, and it's constantly equal to the required centripetal force. Fine. So this point in the green box, the magnitude of the resultant centripetal force is constant, but its components vary. Okay, so at A, the normal contact force, the tension, acts in the same direction as the weight. So I've labeled it as T here, but let's change it to R. Because I was assuming the sort of spokes were providing tension, but instead it looks like it's on some sort of fixed disc, and that's what's providing the weight. Fine, I don't mind. So A, R plus mg are going to be equal to our centripetal force. Nice. As a result, R doesn't need to be very big. It can be quite small. At B, R acts perpendicular to the weight, so it doesn't really have an effect. Or the weight doesn't have an effect. So R is exactly equal to the centripetal force, because the weight is busy, acting perpendicular to it. At C, I'm afraid R has to act against the weight. R minus mg is equal to Fc. The size of Fc is constant. So what changes is the magnitude of R. R is a reactionary force in this instance. It changes its size as the carriage goes around the wheel. Magic. Okie dokie. How we do for time? Let's push on a little bit faster. I think there's too much dilly-dallying about technical difficulties. Inside a washing machine, a sock spins around in a vertical circle stuck to the inside drum. Explain how the normal reaction force acting on the sock varies as it completes the circle. 3 marks, we want 3 different points. Very similar to the previous slide. We had 3 points, A, B, and C. Maybe that's a good structure to follow. It's only in bullet points, so don't write fancy sentences. But each point we keep it focused on the normal reaction force. We are explaining, that's our command word, but keep it specific to the normal reaction force. We don't necessarily need to know the weight. So the normal reaction force always points perpendicular to the surface of the drum, towards the center of the drum. Good, that's a general description. The magnitude of the normal force is maximum at the bottom of the drum, as it has to oppose the weight and provide centripetal force. And the magnitude is at a minimum at the top, because it acts, it provides only parts of the centripetal force, as the weight helps the war effort. Right, so much for circular motion. Let's then talk about simple harmonic motion, which I said is a mathematical analog. It uses a lot of the same concepts. It uses angular speed and so on and so forth. But remember that although they are related, they're cousins, they're not the same thing. Not quite. Okay, so instead of traveling literally in circles, we are doing some sort of periodic movement. So maybe we're going backwards and forwards. Child on a swing is the classic. So it starts, the child accelerates, forwards, and he goes through the middle, where he's at his equilibrium position. And then at the end, he's accelerating backwards. He might still be going forwards as he approaches the very front of his swing, but he started to accelerate backwards. He started to slow down. The maximum speed is when he's in the middle. That's the real whoosh of the swing. So when we talk about simple harmonic motion, you don't necessarily need to interrogate each word within SHM, but you need only understand that it's oscillating motion of an object with a specific mathematical format. Have I frozen? Yeah, there we go. Sorry, my PowerPoint was playing up for a little bit there. Which has the following two features. The magnitude of the acceleration is proportional to the negative displacement. And so the two features are that it's proportional to the displacement and it's always pointing in the opposite direction as the displacement. So anytime you have a system where the acceleration is proportional to the negative displacement, you can guarantee that you're going to have simple harmonic motion. And this happens perhaps more often than you would think. Okay, if we said acceleration, look, there's direct proportionality between a and minus x. We are at liberty then to say that a is equal to negative kx, where we can make up our own constant of proportionality. Now, for reasons that will be mathematically convenient later, so this is a choice that is based purely on mathematical convenience for now, but our constant of proportionality, we are going to choose to be this thing called omega squared. And that is because that will turn out to be, omega will turn out to be our good old friend, angular frequency. Now you might at this stage say, James, look, I thought omega was angular speed. And you're right. In the context of circles, it is angular speed. In simple harmonic motion, we instead call it angular frequency. And that's because when you talk about a circle, you really are talking about sort of how fast around the circle you're going. It's a bit more complicated in simple harmonic motion. This is one of the reasons I say they're not the same thing, even though they have mathematical analogues and they're related. The boy on the swing is not always turning through a physical angle at the same rate. You know, there's a moment where he stops, there's a moment where he goes at his maximum speed, and so on and so forth. So instead of physically splitting a circle up into 2 pi radians, we're going to conceptually split up a motion, a repeated motion, into 2 pi segments, and say how far through a repeated motion is he? If he's halfway, well, then he's pi radians through that motion. And then if he's all the way through that motion, he's at 2 pi radians, ready to start again. So similar but related concepts. Okay, all the maths from before still applies, don't worry. So omega is still equal to 2 pi, and that's still equal to 2 pi over t. Great, so don't chuck away your maths. The maths is still useful. The maximum displacement from the equilibrium position, we are also going to define as A. So for example, if I have a mass on a spring, and I pull it down and then I release it, it's got an equilibrium position here. And perhaps its maximum position is up here. Ding, 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 ding. It sort of springs back and forwards. The amplitude, and it's important to make this distinction. The amplitude is not the full range from the peak to the trough. It is the maximum displacement from the equilibrium position. Okay, so it's only this distance. It is not from here all the way up to here. A is independent of the time period t of the oscillation. So whether my spring or my child or whatever this system is, whether it's doing massive oscillations or very little ones, its time period is the same. So if it takes 1 second to do a little one, even the massive one, it will still take 1 second. Okay. Right, so the amplitude is the maximum value that x, our displacement, will take. If x is our displacement at a given time, a is the maximum value of that displacement. Okay, so at some point, we will get the situation where the maximum acceleration we can get, if we look at this equation back up here, the maximum acceleration we can get is minus omega squared of the maximum displacement, which we've defined as A, our amplitude. Okay, I promise, we'll bring all these concepts together further in just a moment. An example of a simple harmonic oscillator is a mass m on a spring with spring constant k. Okay, yep, this makes sense. The force here is equal to minus kx. Therefore, the acceleration is minus k over mx. Therefore, you can see the acceleration is proportional to negative x. Therefore, we're going to get our simple harmonic motion. Here is its equilibrium point. Here is it when it's at its maximum displacement. Here is it when it's at some intermediate form of displacement. Okay. Again, some of these the formula for these two systems are given on your data sheet. For the purposes of today, we're going to have to move a little faster, but you do not need to necessarily worry about deriving these. You're given them in your formula sheet, but you're given that the frequency, bear in mind not the angular frequency, just the frequency f, is equal to those two systems. Okay. You can then use all the maths we've covered so far, multiply the frequency by 2 pi, and you'll get the angular frequency, and so on and so forth. Okay, exam question. Describe and explain how the period and maximum acceleration of the oscillation of a pendulum depends on its initial displacement. Okay, 2 marks, 1 mark for describe, 1 mark for explain. The period, so if you're given this for a pendulum, the period is going to be 1 over f. So the period will be 2 pi L over G. So it depends on what planet you're on, because it depends on the gravitational constant or the gravitational acceleration. And it depends on the length of the string, but actually it doesn't really depend on anything else. Initial displacement determines amplitude A, and period is independent of this. Maximum acceleration is given by A max is minus omega squared A. Since omega is independent from A max is proportional to the initial displacement. Okay. So the period does not depend on the initial displacement, but the maximum acceleration does, because acceleration for all simple harmonic motion systems is proportional to displacement. So the maximum acceleration is going to be proportional to the maximum acceleration, maximum displacement, i.e. the amplitude. Okay, SHM graphs. How much? Okay, yeah. Okay, right, so let's push on. We want to find a solution for x which satisfies our simple harmonic motion equation. So far, it's been a little unsatisfying. We've said, look, the acceleration is equal to some constant proportionality times minus x. But we haven't given a function in terms of time for, well, what does x actually look like? What's the graph of simple harmonic motion? This equation is a differential equation, because acceleration, for those who do A-level maths, you will know that acceleration is displacement twice differentiated with respect to time. Velocity is displacement over time, but then acceleration is velocity over time. The net result is that acceleration is grab displacement and then differentiated twice with respect to time. So the real equation you're trying to solve here for x is this horrible linear equation. I need a function of time, x to be a function of time, such that when I differentiate it twice, it equals itself, but negative. What function satisfies that? It is cosine, or indeed either of the trigonometric functions. So it can either be cosine or sine. Sine differentiated by t is cosine, differentiated again is minus cosine, minus sine. Fab. Great, and this is why the use of omega squared is also mathematically useful, because it forms part of our solution. If we differentiate this function via the product rule, we have to bring out omega in front. Apologies if you don't do A-level maths. If you don't do A-level maths, you don't necessarily need to understand the differentiation aspect of this. You just need to understand, look, there's this equation that mathematicians can solve, and the answer is this, this, and this for the displacement, velocity, and acceleration. Okay. And if we plot this, we end up with amplitude here. You can see our period here. And all's well. And you can see, look, A actually is equal to the same thing as X, but it's negative and it's got this omega squared in front of it. So hooray, it does satisfy that differential equation. If I plot, then I've plotted X here. How then can I plot velocity? Well, I can consider the gradient. At t equals 0, what's the gradient of x? It is 0. Therefore, for velocity, it must start at 0. At this point, the velocity, the gradient of x is maximum. It says it's steepest and it's negative. Therefore, at this point in time on my graph of v must be at its lowest point, and so on and so forth. And you can just by looking at the gradient of this graph, you can plot this graph and then repeat the same trick with v. I can see at this point, for example, I can say, look, I can see that the gradient is 0. So if I find this point on my x-axis for the acceleration graph, lo and behold, I can see, look, yes, it really is 0, because each of these is the gradient of its predecessor. We plot a graph, and then we plot a graph of the gradient of our first graph. Right. So x max equals a, and that is at t equals 0 or 1 period, or a whole number of periods. And I could rewrite that as n over f. Yeah. But I also know that omega is 2 pi f. So I could also write that as t equals 0 or some integer times 2 pi over the angular frequency. 2 pi n over omega. That's when you'll have maximum displacement. And it will repeat forever and ever and ever. Okay, what about our maximum velocity? When do we get our fastest motion? And what is the value? Well, the value, just looking at this mathematical function, sine and cosine, these two trigonometric functions, they always take values between -1 and 1. They can't ever be greater in magnitude than 1. So they're not super extreme. So what's the maximum value? Well, the maximum value of this that it can be is 1. So the maximum value of V that can take in terms of magnitude is A times omega. And that's going to be whenever x is 0. Because whenever x passes through the equilibrium point, that's when its gradient is steepest. Therefore, that's when the max velocity is. Okay. What about A? When's the maximum acceleration? And what's its value? Its value, using a similar trick, the maximum value that cosine as a function can take is 1. So the maximum magnitude of acceleration is A omega squared. And this always occurs when the maximum positive acceleration occurs when x is at its maximum negative displacement, and vice versa. So it occurs when x is equal to minus a. I'll say plus or minus a, as long as you reverse the sign. So when x is at minus a, the acceleration will be at its positive maximum. When x is at its highest point, the acceleration will be at its negative maximum magnitude. Okay. Does that stand to reason? Think about your girl on the swing. When x is at its positive, maximum, so the girl is, or the boy or whatever, is swinging at when x is a max, so it's at fully forwards. What is the acceleration doing? It's at its maximum value pointing backwards. That is what happens. And when the swing is at the displacement is at its maximum negative displacement, what's the acceleration doing? It's at its maximum value, but it's pointing forwards. Okay, so that does square with our graphs. The displacement and the acceleration are always pointing opposite directions, which is a good thing, because that is exactly that's what this equation up here is saying. It is saying, look, they're always going to be pointing in opposite directions. Okay, for a simple harmonic mass spring system, we can write equations for the energy of the system. Again, we won't worry with the derivation for this equation, but the energy of a spring is half kx squared. And that is that's elastic potential energy stored in spring. Okay, so when the spring is maximally extended, all the energy is stored as elastic potential. So when we're at extremes of x, the elastic potential, this green line, is at a maximum. Hooray! So here's minus a, here's plus a. However, in between, you get, where does the energy go? Obviously, it dips. It's converted into kinetic energy. If I boldly attempt to draw kinetic energy, that's not such a good parabola. That's arguably a slightly better one. The kinetic energy, as I hope we all know, is half v squared. And the total then is half kx squared plus half v squared. And it's a constant. This faint red line up here is the total energy. Fab. It's a closed system, so we can't create or destroy energy. And I've jumped ahead of myself. I should have looked on the next page of the notes. But just as I said on the previous slide, the kinetic energy is always going to be, the total energy will be, well, it takes the maximum value here. I said this was minus A, and this was A. What value does the potential energy have here? It's half K A squared at its maximum. Therefore, that is going to be mathematically, these are all constants, half K and A are all constants. That is going to be our numerical value for the total energy. And you subtract from that half Kx squared. And there's an alternate expression for your kinetic energy. If you then set it equal, do this, you can work out an expression for V. The halves cancel. You will need to square root, but you get half K over M A squared minus X squared. And if you are wondering, but we can then say, look, from a few slides ago, we know that omega squared is equal to K over M. Or rather, I think it actually said that omega is the square root of K over M, but hopefully you can recognize those are the same thing. If this is omega squared here, we can take that out. We can say, look, V is plus or minus omega times the square root of A squared minus X. What does that look like as a function? It looks like that blue line. If you get Wolfram alpha out or whatever and plot that function, you'll get an inverted parabola with a maximum value of omega A squared. Okay. Okie dokie. We might actually have to skip that exam question just because we've got one more. Two more quick things to say before our break, and I don't want to delay your lunch. But as I say, you'll get all the answers at the end of the day. Right, we've talked about oscillating systems, do repeated motion. Let's start to mess around with them. Let's do a little bit of damping. So over time, these systems aren't really closed. They'll start to lose energy to the air around them as thermal energy through drag and friction. And so you get this decaying envelope. Instead of our beautiful sine wave maintaining its amplitude forever and ever and ever, the amplitude decays in this little exponential pattern. And so there's three different types of damping. There's light damping or under damping, heavy damping or over damping. And then the sweet spot, the Goldilocks level of damping, which is critical damping. And I just want to remind you that throughout all of these, the period does not change. The time period is constant. Okay, and that graph you can see there is the case of light damping if you have this exponential decay. Okay, so light damping is when the resistor's forces are small. The time period remains constant. Sorry, I just want to correct myself. I said the time period is constant. Time period is constant for the case of light damping or under damping, as this slide will clarify. So characteristics of light damping are the amplitude decays exponentially, and the time period remains constant. If you are exerting heavy damping, your period essentially it almost disappears. You don't really have oscillation motion. You'll see on the next slide when we give you a graph, is that it stops oscillating. There's a potential for no oscillations to occur at all. So of course the period is affected, and the amplitude decreases, as you might expect. Critical damping, because when you Goldilocks level, just right, the system returns to equilibrium in the shortest time possible without any oscillation. So again, no period. Why is this important? So for example, car suspension, if our car encounters a sudden shock, we don't want it to be bouncing around for ages. We don't, and that rules out light damping. We want it to return to a stable position as soon as possible, and that rules out heavy damping, which is shown in green. The best is critical damping, because we'll get it just right and we'll return back to our equilibrium state as fast as possible. So this tends to 0 in the shortest time. Okay, again, we will push past this question. Damping is essentially a small practical concession on our syllabus. 2 more slides of substantive content, and then I promise I will let you go for lunch. Don't worry. Right, resonance. This is important. So I promised that we've got our simple harmonic motion and we're starting to interfere with it, either by changing the medium through which it's going. Maybe you're damping it by, you're filling your car suspension with fluid, or maybe you're messing with the spring to exert a certain amount of damping. But you can also start applying external forces to it. So we had our child on a swing or a pendulum in a clock. If I start periodically giving it a push, there's 2 things I can change. I can change how much force I use. I can change when I give it a push. And particularly we're interested in how often I give it a push, its frequency. If the child, or whatever it is left alone to their own devices, they will oscillate at what is called the natural frequency. Natural frequency is the frequency with which they will oscillate if there's no external force. When a driving frequency, that's the frequency with which I am pushing. It's an applied frequency external to the simple harmonic oscillator. When the driving frequency is equal to the natural frequency, this sudden increase in the amplitude of our oscillations occurs, and that's called resonance. So if you get it just right, the driving frequency, you can match the natural frequency and you can get far more motion, far more excitement for the child than you otherwise would have. During resonance, the application of the driving force is timed such that it increases the amplitude. How much can it increase the amplitude? Well, quite a lot. So here we have the natural frequency, this central dotted line. And in red, we have undamped. And what we are plotting here is the amplitude, so the maximum displacement as we apply a range of driving frequencies. So if we get it and we match it to the natural frequency, you can see the amplitude goes very high indeed. If you've ever seen the video of the Tacoma Narrows Bridge, where it starts wobbling because the wind strikes the bridge with a driving frequency equal to the bridge's natural frequency, and it means the whole bridge collapses. That's exactly what's going on there. As we proceed to then, so we can do both things. We can apply the driving frequency and we can damp it. So we're progressing. So undamped, lightly damped, and then sort of progressively heavier damped. We will see that we have this split off line. This is the resonant frequency. Okay, so as you start to damp, It's not universally the case that the resonant frequency is always equal to the natural frequency. That's the true if it's undamped. But once you start damping, the resonant frequency starts deviating from the natural frequency.